Imagine a wealthy investor hands you 10,000 top-tier GPUs for 1 month. Your goal is to build a highly capable, open-source language model. Before you boot up a single server, you have to make choices. What architecture will you use? How will you mix training data? Guessing these hyperparameters is risky. If you guess wrong, the entire budget is wasted on a model that barely works. To avoid that disaster, researchers rely on scaling laws. These are simple predictive rules that allow engineers to test variables on tiny, cheap models and accurately calculate how those exact same settings will behave at massive scales. This chart shows model error plotted against computing resources. On a standard graph, the learning curve looks chaotic, but when we map it on a log-log plot, where both axes increase by multiples, that chaos resolves into a straight, highly predictable trend line. Because that trend line holds true across multiple orders of magnitude, designing an AI becomes a reliable mathematical engineering blueprint. While massive language models are new, the math used to predict their behavior actually traces back to academic statistical theory from the early 1990s. Decades ago, theorists established classical generalization bounds. They proved that for standard statistical tasks, a model's error rate decays in a highly predictable polynomial pattern based on the sample size, often measured as an inverse fraction like 1/n. Despite their massive scale and black box complexity, modern neural networks obey the exact same rules. They learn slower, often scaling at fractional rates like 1/10, but their error rates decay along the identical mathematical curves discovered 30 years ago. The most straightforward rule in AI engineering is the univariate data scaling law. If you hold your model size constant and simply increase the volume of training data, the error rate predictably drops. This graph shows the effect of changing the quality of that training data. If an engineer finds a better mixture of high-quality text, the starting point of the error, the intercept, drops significantly. But notice the angle. The overall rate of learning, the slope of the line, remains identical. There are hard limits to this math. If you run out of fresh text and decide to repeat your existing dataset, the model keeps learning up to a strict limit. Once you show the network the exact same text more than 4 times, the predictive scaling law breaks and performance flatlines completely. This creates a moving target. At small scales, engineers strictly filter data to keep only top-tier text, but as a lab's compute budget scales up, they will exhaust that premium supply. To avoid the repetition penalty, the filtering strategy must dynamically loosen to accept lower quality data. Pre-training optimization requires calculating the precise mathematical threshold where gathering more data, or repeating what you already have, yields diminishing returns. Scaling laws also dictate structural design choices. By plotting performance across a few cheap training runs, engineers can definitively prove why modern labs invest in transformers over legacy architectures like LSTMs, locking in the most efficient design early on. This visual scale demonstrates the concept of critical batch size. Engineers must find a perfect equilibrium between 2 opposing forces, reducing the gradient noise, or variance, and minimizing the risk of the model stepping in the wrong direction, known as bias. Finding this mathematical sweet spot allows engineers to process the largest possible batch size. It pushes the hardware to its absolute maximum limit, keeping parallel processors fully fed without suffering any drops in performance. The learning rate obeys a similar structural rule. As the physical width of a model's architecture increases to absorb more complex patterns, the optimal learning rate must predictably shrink. These laws do come with a major caveat. Achieving perfectly predicted scores on an upstream objective, like predicting the next word, does not guarantee the model performs flawlessly on downstream, real-world tasks like logic puzzles or coding. While scaling laws perfectly map the internal mechanical efficiency of a model, an engineer must still validate that those mathematical curves translate to actual capabilities. Every massive training run operates under an isoflops constraint. You have a strictly capped compute budget. The defining decision is how to spend it. Do you gather more data, or do you build a bigger model? In 2020, OpenAI addressed this with the Kaplan scaling laws. Their original predictions argued that as your budget grows, your model's parameter count should grow significantly faster than your training data volume. That strategy drove the industry until 2022, when DeepMind published the Chinchilla paper. They corrected the math, proving the optimal balance is actually an equal scaling ratio, 20 tokens of training data for every single model parameter. The original Kaplan prediction failed due to micro-oversights at the smallest testing scales. They had excluded certain embedding parameters from their counts and measured models before their warm-up phases had fully stabilized. Because scaling laws are exponential multipliers, a tiny miscalculation in the initial testing phase multiplies outward, resulting in massive, inefficient models that waste millions of dollars in compute. Today, frontier labs intentionally ignore the optimal Chinchilla ratio. They rely on a strategy called overtraining. By spending extra upfront compute to train a smaller model on massive amounts of data, they create a highly capable system that takes far less processing power to run. This solves the actual long-term financial bottleneck, serving the model to millions of end users. The ultimate goal of scaling laws is engineering the most economically viable model for real-world deployment. If you want to move from theory to practical building, head over to the Learn by Doing with Stephen channel, where we tackle the exact mechanics of deploying these AI models. And to dive deeper into the massive datasets powering these scaling laws, check out the Stephen Data Talk podcast, available now on Spotify and YouTube Music.